Okay, let's start class. So last time we talked about the logistic regression with the for the sparse data case. If we have a sparse data case, we can have the infinite parameter estimate. And also we talk about the residual analysis, diagnostics, and we talk about even though in some case, since we have some like perfect separation or quasi-complete separation, the beta that we estimated is infinite value, but we can still do the inference, such as do the hypothesis test, as well as the confidence intervals on that beta. Okay, it's still possible. Okay, so today we will talk about the rest of the material in chapter 5, and hopefully we can finish that in today's class. So section 5.4 is about alternative approach for logistic regression. And one of the main alternative approach for the logistic regression is the Bayesian modeling. So far we only talk about the frequentist approach, okay? But Bayesian approach becomes more and more popular. Why? Because the Bayesian statistic is a framework that can update our subjective knowledge, update our belief about the parameter of interest according to the data that we observed. So you can see the Bayesian framework is very natural to inject the subjective knowledge into the model, into the modeling process. So that's why Bayesian statistics is especially popular when we have limited sample size. Okay. Why I say it's especially useful in the limited, because if you have large enough samples, the frequentist will, so the data will tell all the stories if we have large enough samples, right? So if we have a relatively small sample size, or if the cost of collecting data is very expensive, then we cannot get as many as we like. So in that way, the information that we observed is limited. So that is give us, so that tell us that if we have any subjective knowledge, we should incorporate so that we can have a better estimate. Okay. So the Bayesian models include a few parts. One is the prior distribution that encapsulate the prior knowledge or the belief about the parameter values before we collecting the data. Okay, and the likelihood function represents the probability of observing the data based on a certain set value for the parameters. Okay, and the posterior distribution is the updated distribution on the parameter of interest. Okay, so based on the Bayes theorem, we know that so this pi theta, that's the prior distribution. That's our belief or the subjective knowledge on the parameters. multiplied by the likelihood function. D, theta is the parameter of interest. D is for data. Okay, D includes X and Y's, whatever. So these are the observed data. D is observed data. So likelihood function gives the probability of observing the data that we got, given a set value for the parameters. Okay, and divided by MD. M is the marginal distribution for the D. And it is equivalent to this is the posterior distribution of theta given D. So that is our updated belief on the theta after we have the data observed. So this equation is just the Bayes theorem, right? If you know the Bayes theorem, you can easily see that. Okay, so we need to, so in the Bayesian modeling, these are the three components: the prior distribution, the likelihood function, the marginal distribution of the data. And then we can get, and then we can update it, our knowledge on the parameters of interest based on the data we have. Okay, so that is the whole theoretical foundation for the Bayesian statistics. But you know, the formula is easy, and we can specify the distributions, this. But it is very common that we don't have a closed form for the posterior distribution. Okay, for example, if we have a normal prior on the theta and the likelihood function follows a normal or the Gaussian distribution, and then we can easily show that the posterior is also normal. Okay, and for normal distribution, we can write out the exact PDF, the probability density function. We can write that out. So that is a closed form. But what if the prior is not normal? Is a different distribution, so that it is very likely that we cannot write out the exact PDF. There's no such closed form. Okay, so how can we estimate the posterior distribution? We can estimate through a technique which is commonly used in Bayesian, that's called MCMC, Markov chain Monte Carlo. Okay, so this MCMC is used to approximate those posterior distribution that has no closed form. And then we can make the inference and we can make the predictions for the Bayesian models based on these MCMC results. Okay, so if you look at the weekly schedule, so this week, right now we are here. So we will finish we are scheduled to finish the chapter 5 today. And then next week, we will talk about chapter 6. And the week after next, we will talk about chapter 7. Then we will have a spring break. After the spring break, we will have our second midterm. So that covers chapter 4 to 6. So you can start it to prepare for the exam 2. And after that, we will have 3 lectures on the Bayesian. So I will leave this to these 3 lectures after the exam 2. Okay, so Dr. Guo in our department, she will talk more details on the Bayesian approach on the data categorical data analysis. Okay. Okay, so another alternative approach to for the logistic regression is the penalized likelihood approach, which is also very commonly used. So for the penalized approach, that actually is called regularization method. So regularization, this is a term originally come from mathematics. There's a Russian mathematician Tikhonov. He developed, he started the regularization idea. So the original motivation for the regularization is some mathematics problems are ill-posed. That means we cannot find a unique solution. Okay, so in other words, so then he just used the regularizations idea to add some constraints so that it guarantees the solution is available and unique. Okay, so that's originally it was used in mathematics, but statisticians adopt this idea in the statistical modelings, and this becomes a very, very popular idea. Especially nowadays, regularizations idea has been used everywhere. For example, like the chat GPTs, these artificial neural network, deep learnings, machine learning algorithms, complicated statistical models, all of these, they use the regularization idea somewhere in the algorithms. Okay, why? Because the regularization is very powerful tool to overcome the overfittings. And also regularizations can guarantee that the solution is unique, is available there. And third is it makes the solution very stable. Stable means that if you change the data slightly, the solution will not change a lot. Okay, so there are many benefits that you use the regularization approach. Okay, so that's why the regularized logistic regressions is another way that we can use in in practice. So there are actually many regularization approach methods in for the logistic regressions, such as we can use lasso based logistic regression, the ridge based logistic regressions. Okay, but here in this course, we only focused on regularizing one particular regularization method for the logistic regression that was developed by the statistician David First. He proposed penalized likelihood correction that reduced the bias in logistic regressions. Okay. Uh, the motivation for this approach is Dr. First, he added an extra term to the likelihood function and trying to maximize the likelihood plus that extra term so that it can reduce the bias and also can stabilize the solutions for the logistic regression models. Okay, and this is particularly powerful when we have those sparse data issues. For example, if the data is quasi-complete, some of the parameters cannot be estimated, or some of the parameters have infinite values. Then, using this penalized likelihood approach, we can guarantee to have a non-infinite value estimate for that parameter. And also we can have some reasonably good confidence intervals based on this penalized approach. Okay, so I won't talk about the details because the details will be too technical. So let's just see an example. Okay, so go back to the endometrial cancer example, which I mentioned in the last class. So we know this data set has a quasi-complete separations, right? So in this data set, the response variable is the HG, okay? And this is a binary response. And we have 3 predictors, okay? And these two, the PI2 and EH2, these are the continuous predictors. But the NV, that is the binary. And that is the variable that we have a quasi-complete separation. Remember that we talked about last time? So if we use the ordinary logistic regressions, we will either, some of the software will just give you the infinite value for the beta NV. Some of the software will give you some finite value, but with huge standard error, because the likelihood function is so flat that the variation is so large that basically it tells you we cannot estimate the beta for the NV. Remember that I showed you in the R last time. So the NV has over 1,000 for the standard error. Okay, but here, if you use the library Logistic F, that is the package can implement the David First penalized likelihood method. Okay, and in that package, there's a function which is the same as the name of the package called the Logistic F, and you apply that, and you can see this time the MV2 has the coefficient value is 2.93. And look at the standard error. It's not infinite. It's not huge. It's just 1.46. And it gives you the 95 or the 90% confidence interval. It's lower 0.95 and upper 0.95. So that's 90%. Why it's 90? Because we leave 5% lower end, 5% upper end. So in the middle, we have 90%, right? So that's the confidence interval, 90% confidence interval. So you can see the confidence interval is also has a finite width. Okay, and also it gives you the test statistic and the p-value for the likelihood ratio test for that term. So you can see the NV2 is significant, and we have a finite confidence interval and a finite estimate. Everything seems much reasonable than the ordinary logistic regression results. So this just gives you an example that we can use the first penalized likelihood approach to handle those sparse data issues. Okay. Okay, now let's talk about the effects of small samples on the Pearson's chi-square test and the likelihood ratio test. Okay, so for the binary response with only categorical predictors, the goodness of fit tests are approximately chi-squared for large N. And that approximation, the quality of the approximation really depends on the N and the number of cells. N is the total sample size, N is and also the number of cells. Okay, it improves so the quality of the approximation to the chi-square distribution becomes better and better if the average count per cell increases. In other words, the best quality of approximation happens when we have each cell, on the average, we have more and more counts. And that will approximate to the chi-square distribution very well. Okay. However, if in practice you have some cells that have very low counts in some cells. For example, you have one observation at a particular cell, that is permissible, that is okay, as long as these kind of cells will not take like 20% of the total number of cells. Okay, and the rest of the over 80% of the cells, they should have the fitted values is no less than 5. So most of the cells should have the counts is greater than 5. And just one or two, just a small portion that is less than 5, that is okay. And that is for the Pearson's chi-square. And we know that the Pearson's chi-square test tends to be more valid with small sample case and the sparse tables compared to the like ratio test. Okay, remember we talked about that in the chapter 2, right? So that is the Pearson's chi-square test study. That is the like ratio test for the tables to test independence, right? So for fixed value of n and the number of cells, when we compare the two models, okay, suppose we have a data set, the response is binary, and the predictors are also categorical. Okay, so we have fixed number of m's and cells. Okay, so the chi-square approximation will be better with small value of degrees of freedom. What does that mean? That means so the condition is very important. Given the n is the same and number of cells are the same. So when we compare two models, okay, let's say this is model 2, this is model 1, right? So this is degree of freedom, df1, this is df2. Okay, so what is the, let's say this is more complicated model. This is the simple model, okay? And these are the residual degrees of freedom. So the test statistics has the degrees of freedom is what? Is equals to what? This is a simple model. M1 is simple model, so the df1 is larger. That's the residual degree of freedom, right? So it should be df1 minus df2. So that is the degree of freedom for the chi-square test. Is that right? And what is the test statistic? The test statistic is the deviance for the model 1 minus the deviance for the model 2. So that's the test statistic, and that's the degree of freedom for the test, right? So for fixed n and number of cells, if this one is small, the approximation is better. If this one is small, that the chi-square approximation is better. In other words, if you compare two models which only differs by one parameter, 2 parameters, then that approximation, that chi-square approximation is much better. Then you compare one model with another model, which the difference of the parameter will be like 10, 20, then that approximation will be very poor. Okay, so that's what it meant here. And the last one is when the cell counts are very small. Sometimes we can combine the categories of variables. Let's say in one data set, we have 5 class. Let's say we have 12 class for one of the predictors. Okay, and that predictor is the months. Okay, so we have 12 months from January to December. Each month is a category, right? And because of this predictor has too many classes, 12 classes, So the average count for each cell becomes very low because we have so many cells. And that approximation for the chi-square test or the likelihood ratio test is not good, right? So what we can do is we can merge some of the class as a bigger class. For example, for the months, there's a natural way to merge it into what? Into 4 seasons. Let's say we have spring, summer, fall, and winter. In that way, instead of 12 class, we have 4 class. Merge 3 months into 1 class. So in that way, we can increase the cell counts to make the approximation better. Okay, but you have to be very careful to use this approach because it's not advisable unless there is a natural way to combine them and the little information loss in defining the variable more crudely. So you have to be very careful, okay? So to use this approach. Okay, any questions so far? Okay, the next one, the chapter 5.45, that is another alternative approach to the logistic regression, and that is called conditional logistic regression. Okay, and by its name, you can easily see that it is not based on the likelihood. It is based on what? Conditional likelihood. Okay, and you may ask, what does conditional mean? And you will see that in a minute. So when the n is small, when we have limited sample size, or when the number of parameters is large, okay? So the question is, are we really interested in all these parameters or not? If we have a large number of parameters. If we are not interested in all of them, if we are only interested in, let's say, 1 or 2 of the parameter, and the rest, we just acknowledge them, we are not interested in their values, but we just acknowledge them and use them as like a block variable in the randomized block design that I mentioned before. So in that way, these parameters not of interest is called a nuisance parameter. Okay? And the parameter that of interest is only 1 or 2. So in that case, in this situation, then we can use a very, very powerful technique called a conditional logistic regression. And that can estimate, allow us to estimate and also do the statistical inference only on those parameters of interest. Okay, so let's see an example. For example, in a longitudinal study, what is longitudinal study? So longitudinal study, let's say we have 100 patients, okay? And we give these patients some treatments throughout the time. And we do the measurements also throughout the time. So each patient, we have, let's say, 12 measurements. Each measurement is happened every month. So we follow that patient for a year. Okay, so we have monthly data for that person, for that patient for 12 months. Okay, so we have 100 patients. So we have 100 that curves. And this is a longitudinal study. Okay, so we follow the subject, do the multiple measurements throughout the time. So in this longitudinal study, we have the response is YIT. Okay, what is I? I is the index for the subject, right? Let's say I is ranges from 1 through 100 because we have 100 patients, right? And what is T? T is the index for the time. So as I said, if we measure 12 months, so T ranges from what? T ranges from month 2 to the month 12. Is that right? So that's the range for the T. Okay? So X is the explanatory variable for the person, for the patient I at time T. So let's say X is the let's say is the what's that called? Uh, the some like the blood pressures or some other values we also measure throughout the time, and these can be used as the predictors that will affect the outcome. Why? Okay, so in that case, we have a model for each person, right? We have the logit, and the y is binary, as I said. So here the logit on the y equals to alpha I plus beta times xit. So you can see if that model is for what? Is for the each person, is for the I's subject. And I is ranged from what? We have 1 through 100. We have 100 patients, let's say, right? And here, what is alpha I? Alpha I is the individual specific intercept on the logit. And you may ask, why? Why we need to have a intercept which depends on which is different for each individual? And that's very common in practice. Why? Because you can see different patients, they have different conditions, right? Like the gender, weight, height, race, and like the dietary behaviors are different, exercises, conditions are very different. So they are very different. And we should acknowledge the individual to individual variation. Does that make sense? We know that for those clinical trials, the individual to individual variation is a lot, right? But do we really interested in to estimate the alpha I? No, we don't. What we really interested in is to estimate the effect on that particular predictor X. And that is our main interest. Okay, so in that case, we have 100%, right? And here, look at the next term, the beta xit. So here, the effect on the X does not change over the individuals. So we acknowledge the individual to individual variation through the alpha I. However, we assume that the effect of the treatment X is universal, is the same to all the subjects. Okay, so how many parameters do we have in this data? We have 100 subjects. So how many alpha I's do we have? We have 100 alpha I, is that right? Plus we have 1 beta. So how many parameters do we have? We have 101 parameters. And how many samples do we have? We only have 100 samples, 100 observations, 100 subjects, I'm sorry. So here, to estimate these alpha and beta simultaneously, that is very difficult. And that can cause lots of overfitting, instability on the estimate. But the point is not just the poor quality of the estimate on these parameters. The point is we are not really interested in the alpha I's. For this subject, alpha I is large, that's fine. we only interested in the beta, right? So if we use the ordinary logistic regression, we just estimate alpha and betas simultaneously, and then do the inference on beta. And that inference you will see in a minute will be very, very different from the true values or from the conditional logistic regression. So what conditional logistic regression does is it will not estimate those alphas. It will only estimate the betas. And it gives you the exact estimate. It gives you the inference, like the standard errors and the confidence intervals and the likelihood ratio test on the betas. It will give you all of these, except it won't give you it cannot estimate alpha. And that's conditional logistic regression, okay, which is very useful in here, right? And you may ask why and how does the conditional logistic regression can estimate the beta without estimating the alpha? Okay, so that is a question, right? So that is the purpose for the next slides. So I will show you, but you don't have to know. Okay, that just I taught this last year, and I didn't include that slide, and several students asked me that question. So that's why I have to give you some simple examples to convince some of you, okay, which is curious about why the conditional logistic regression can estimate the beta without estimating the alpha, because it all cancels out. Okay, so here, for the illustration purpose, I'm just giving you the simple case. Otherwise, it's too complicated. So the simplest case I can think about is one-to-one matched study with K-stratum. Okay, so let's say we have a match-controlled study. Okay, so the response is binary. Let's say Y is the cancer status. Okay, let's say the Y is prostate cancer. If the subject has the Y1K is 1, that means this patient has prostate cancer. And the Y0K, that means this patient has no prostate cancer. So here we go to the hospital and collect 100, let's say 100 prostate cancer patients. Okay, and these 100, they can have different race, different age, different jobs, so many different conditions, right? And then for each patient with prostate cancer, we also find it's one control which match the age, match like the weight, height, some of these that we can control. Or maybe if some condition also really matters, we also match that. Okay, so we have each patient that has prostate cancer, we have its control that matched some of the case. And then we want to see the smoking effects on the prostate cancer. So let's say the X is smoker or not, or non-smoker. So for each of the stratum, so we have how many stratum do we have? We have 100 stratum. Each stratum, we have 2 subjects. One is prostate cancer, one is control with no prostate cancer. Does that make sense? So we controlled some of the conditions such as the age and so on. But we will ask them, do you smoke or not? Are you a smoker or not? So the smoking status will be the X. Okay, so this is a simple setting. So now let's see the conditional probability for having the prostate cancer given the smoking status X. Okay, and we can write as this one. And you may ask, what is this? This is the logistic regression estimate for the probability. Remember, for the logistic regression, how do we predict the probability? It's the exponential of alpha plus beta x divided by 1 plus exponential of alpha plus beta, right? So that's from the logistic regression. And why it's called conditional likelihood? Because that is what? Within the pair, okay, within this particular stratum. Okay, and within that pair, we have the probability of not having the prostate cancer is this one. Why? Because this is 1 minus this. Is that right? 1 minus this becomes 1 over that. Is that clear? And this is within the stratum. And you may ask why? Because here the alpha k, these are the index for the stratum. And you may ask why we need to condition. Because each stratum, that means each pair, has different control values with other stratum. As I said, each stratum, like the stratum 1, they have a particular age group. Like the 2 subjects in the stratum 1, they are both age is between 30 to 31. And stratum 2, they are in the age 45 and 46. Okay, so you can see we use alpha k to control the stratum effect. So this is conditional likelihood for each k, for each stratum. Okay, so that's why we call it conditional likelihood. Okay, it's conditional on stratum. So then the conditional likelihood for the case stratum is what? So this is the probability, right? So what is the conditional likelihood for the case? So that is the probability of getting 1 given x1k times the probability of 0k equals 0 given x0k. So what does that mean? That means don't forget that in each stratum we have 2 subjects, right? We have 1 subject that has x1k and another subject is x0k. Okay, so 1k subjects, that means this subject is prostate cancer patient. This is control. So the probability of for the x1k have the prostate cancer times the probability of x0k patient has no cancer. Divide by what? Divide by itself. You can see this is the same as the numerator. Is that right? Plus, but don't forget, we have another possible situation. What is that possible situation? That possible situation is, it is also possible, okay, but it's not observed. It is possible, but not observed. That is, the subject X1K person may have a chance to have no prostate cancer. And the X0K subject, they have a chance to get the prostate cancer. Is that right? And that, we also need to include that in the denominator. And that becomes the conditional likelihood for we observe the X1K get the prostate cancer and X0K get the no is a control. Okay, but you may ask, why not both of them have no cancer or both of them has cancer? But don't forget, the sampling scheme is what? One cancer, zero, the other one is no cancer. So it's only possible we can have only one cancer, one no cancer. So that's the only 2 possible situation. And that is the conditional likelihood. Is that clear? So if you are clear about this one, then the rest are just math. That's just simple math. So what is probability of x1k over x equals 1 given x1k? That is here. Is that right? So we just replace this one by plugging the exponential of this. Is that clear? And what about this one? This one is just this one. Just replace the probability by the exponential, by the predicted probability from the logistic regression. And the same thing here. So these are just simple math. And then what we can do is, you can see the denominator are the same in the numerator and in the denominator. So we can cancel them, all of them. Is that right? And then the numerator is exponential of alpha k plus beta x1k. The denominator is exponential of alpha k plus beta x1k plus exponential of alpha k beta x0k. Now you can see what we observe is we have alpha k in common in the numerator and denominator. Is that right? So we can cancel out the alpha k for the numerator and the denominator. So what only left is, that's the amazing part, is we only left this one. You see that? The conditional likelihood is not related to the alpha. So alpha k is gone. So that is the conditional likelihood for the case stratum. So you can see there is no alpha k because we canceled off. Okay, so that's for the case stratum. So how do we find the beta? So the way, so here I give you some solid example to just give you some numeric example that you understand this. Suppose in this pair is this, and the conditional likelihood is that. Okay, so that's just the numeric example to. So then how do we find the beta? So the full conditional likelihood is what? Is the product of all the stratum-specific conditional likelihood. Is that clear? So the full conditional likelihood is what? This is just for the case stratum. Is that right? So the full is the product for k equals 1 to k equals to what? We have, let's say in this data set, we have 100 patients. Oh, 100 stratum. So to the 100. Okay, and that product is called full conditional likelihood. And we find out the beta to maximize what? To maximize the full conditional likelihood. And that's called conditional logistic regression. So conditional logistic regression is not to find the beta that maximize the full log likelihood. Is to maximize the full conditional likelihood. Okay, so that's the difference between the conditional likelihood, conditional logistic regression and the logistic regression. Okay, so, but if you don't understand that, that's totally fine. But I know some of you may be interested in that. So conditional likelihood or conditional logistic regression is a specialized type of logistic regression, usually employed when case subject with a particular condition, okay, or attributes are each matched with one or more controlled subject. So conditional logistic regression provides estimates of the regression coefficient beta associated with the independent variable that varies within at least one strand. So CLR, the conditional logistic regression, can estimate the beta which varies within at least one strata. What does that mean? That means for those, it can estimate those betas which can changes at least in one of the stratum. So just as like the smoking status here, X. Let's say the stratum 1 can have both control and the patient, they both are smoker. And some stratum can have both non-smoker, but some stratum can have one smoker, one non-smoker, right? So the X can change within the stratum. Okay, but so that is the beta we can estimate through the conditional logistic regression. But what are the coefficients cannot be estimated? That is the betas which is constant within the stratum. Okay, so what are the beta that are constant? Just like I said, for this case, let's say if we control the age for each stratum. So age is always a constant within the stratum. Does that make sense? For stratum 1, the age is 35. Then they are both 35. For stratum 2, it's between 45 to 46. So they are all falls into that range. So the age does not change within the stratum. And these parameters cannot be estimated. Is that clear? So that's for the estimate, that's for the beta we cannot estimate for the CLR. Okay, so now let's see an example. And by the way, so this technical part, you don't have to know. Okay, but the rest of the conditional logistic regression, you should know. Okay, so these you should know what can estimate, what cannot estimate. Okay, so let's see an example. So this is the infertility after miscarriage or abortion study. So this is a study conducted in 1976. So to estimate the effect of spontaneous abortion or induced abortion on subsequent risk of infertility. So we have 100 women with secondary infertility. So these are the case. So we have 100 case. And for each case, we matched by 2 healthy controls. It's not 1-1, it's 1-2, okay? So for each case, we have 2 healthy controls. And what do we control? We control the hospital. We control the age. We control the parity, that's the number of pregnancy carried to us, and the level of education. So within each stratum, we have 3 subjects. 1 is the case, 2 is the control. Okay, and for within that stratum, we have the same age group, same parity conditions, same hospitals, same level of education. That's what we control. Okay, but what are the predictors? The predictors are the SP, that's the spontaneous abortion. We have 3 levels, 0, 1, and 2. 2 means 2 or more than 2 number of spontaneous abortion. And also IN, that's the induced abortion that has also 3 categories, 0, 1, 2. 2 means 2 plus, okay? So that's the data. So what are the variables that are constant within each stratum? The variables that are constant within each stratum is the age, parities, hospitals, level of education. These are constant within each stratum. What are the variables that can change, can vary within the stratum? That's the spontaneous and induced. Make sure you understand that. Okay, and the response is the infertility. It has 2 conditions, 0 or 1. Okay, and that is in the case. Okay, case is 1, control is 0. Is that clear? So that's the data set. So now let's say this data is available in R. That data is called infer. And here, this is just some summary statistics for the data. So first, let's just use the regular logistic regression. Okay, just like we only consider the int and the spon. So that's for the induced abortion. That's for the spontaneous abortion. Case is the response. Okay, that shows the infertility, 0 or 1. And you can see through the ordinary logistic regression, okay, ignoring the matching, totally ignore the, the matching and the stratum structure, okay? If we do that, you can see the induced abortion is not significant at all for the ID1, but for the ID2, it's kind of marginally significant. But still, overall, this one is not. And you may ask why we have two levels, two induced, one induced two, and also for the spontaneous SP1, SP2. Why? Because remember we have 3 levels for the spontaneous and 3 levels for the. So 3 levels, we need 2 dummy variables. Okay, and here we set the 0 as the baseline group. Okay, 0 as the baseline group. So SP1, SP2 is the difference from the baseline for group 1 and for SP equals to 1 and SP equals to 2. And the same thing for the induced. Okay? So that's the ordinary logistic regression. Now let's see, we still use the logistic regression, not conditional logistic regression, not. But this time I consider the age, I consider the parity, I consider the education, but not using the stratum structure. We only include the age, parity, and education besides these 2 induced and spun. So these 2 are the variable of what? Interest. We are interested in this. But these 3, we acknowledge them, but not using the stratum structure, just using these 3 variables values and fit it as a regular logistic regression again. But these 3 are called covariate because we are not interested in them, just acknowledge them. Okay, now this time you can see the induced abortion is significant. Both of them actually are highly significant. And look at the size, it is different from the previous one. Okay, so that's the regular logistic regression, but including the covariate. Okay, but this one is conditional logistic regression. For conditional logistic regression, we still only include the induced and the spontaneous. These are the variable of interest. We don't include these 3. However, we include what? We don't include this. However, we include the stratum structure. We use this stratum structure. And using this actually takes care of this. Why? Why? Because the stratum is based on the age, parity, and also the education level. Remember? So this, by using the stratum structure, we've already taken care of those age, education, and the parities. Okay, and here the conditional logistic regression is using the C-logit function in the survival library in the R. Okay, and you can see now this time we have also significant induced abortion effects. And let's compare these 3 approaches together. Okay, so for the unadjusted, that's the first one, ignoring the education parity and that age. Okay, so you can see we have the intercept for this adjust. is the still using the regular logistic regression, but with the age parity and education. So you can see there's some difference in the intercept, but we don't have an intercept term for the conditional. For the conditional logistic regression, we only have these two parameters, in, induction abortion and spontaneous abortions effect. We don't have intercept. We don't have the effect on the age education. Okay, so that's why I don't have that here. But for the induction, or but for the induced abortion, you can, let's compare these three. For the unadjusted, that's the first one, which is very different from these two. For the conditional likelihood of, for the conditional logistic regression estimate and adjusted logistic regression, these two are quite close. You see that? But which one is better? This one is better. Conditional is better. Why? Because that is the right way we do that. That is fitting the models to maximize the conditional likelihood. Okay, that is the right way. So this is the estimate that we should use. Okay, and for the for the IND2, you can see same thing. The adjusted and the conditional are very close, but unadjusted, which is very different. And look at the p-values. These two for the unadjusted are not significant. And for the SP1, SP2, same thing. So without adjusting for matching variables, only spontaneous abortion is significant. But for the after adjusted using the CLR or using the logistic regression, the estimates are close. And the CLR is the one that we should use. Gives the most valid estimate. Okay? Any questions? Okay, so the last one, that's the alternative links for the binary response. So we can have the linear and the probit link. For the linear probability models, we talked about that before. So this is the linear probability models, and but the drawback is the p, the estimated probability can go beyond 0, 1, can be less than 0 or can be greater than 1. So that's the drawback. Okay, so this show you some example. That's actually the snoring and heart disease examples. And the one that noticed mentioned is the first model. The first model is the linear probability model, but here I set the family as quasi. So the quasi family in the R accept the several links such as the logit, probit, and user defined. Like here, I'm using the identity link. So that's the linear probability model. But the user can define the variance. Like here, I'm defining mu times 1 minus mu. Because here, that's the probability. We know that for the binomial distribution, the probability, the variance is what? The variance is p times 1 minus p. Is that right? So that's why I define here as mu times 1 minus. Okay, so the user can define that. So that's the good thing for the using the quasi. And this is the OLS approach. Just treat it as a normally distributed, not binomial, using the identity link. And this is the logistic regression. Okay, so you can see the results. For these two, for the linear model, they have the similar intercept and the slope, but for the logistic, it's very different. Why? Because they have different link function. These two are identity, but this one is the logit link. So that's why it has a big difference. Okay. For the probit, we already talked about that before, but here we are focused on the interpretation for the probit model. Okay, the interpretation for the logit model, that we've already talked about, right? We can interpret the logit model, the logistic regression model through what? Through the odds ratio, through the odds, right? And we can also interpret through the probabilities, and we talked about that weeks ago. But for the probit model, okay, the interpretation is simplest when we relate the model to a corresponding normal linear model through a latent variable. And that is the best way to interpret the probit model. Okay, for example, if let's say the Y is political ideology with 1 is liberal, 0 is conservative. So Y is what? Binary. We have a binary response and we fit the probit model. Okay, but what is a latent variable? Latent variable is, we know that in practice, it's very just the liberal conservative, like here, is not like black and white, right? Some people has extremely liberal. Some people is moderate liberal. Some people is moderate conservative. Some people is extreme conservative. So instead of treat it as 0, 1, black and white, we should use what? It's better maybe to quantify them as a numeric value, right? So we can say let's just use Y star as a latent variable. That is to model the Y through the numeric ways. Okay, so then we can fit a probit model using the Y, still 0 and 1, right? But when we interpret, we can view it as having a latent variable Y star for the observed binary response if we have some unknown threshold. Okay, if let's say, since the Y star is numeric now, and let's say with some unknown threshold, if it's Y star is less than that threshold, it's 0, greater than it's 0, or then it's 1. Okay, that satisfies some ordinary, and the Y star is actually follows an ordinary linear regression model. And that is a good way that we can interpret the probit model. So the probit model, the beta, is actually relates directly to the latent variable Y star. And then but Y star, why is called latent? Because we cannot observe that. We didn't observe Y star. We only observed like the vote results, or 0 or 1. Okay, these binaries. So the Y is what we observed, but Y star is latent, is numeric. Okay, so we can interpret the beta through from the probit model as representing the estimated change in the expected value of the Y star for 1 unit increase in the X, and adjusting for other explanatory. So that's how we interpret the probit model. So let's see the heart disease example again. So here I fit the probit model, and this is the intercept, this is the slope, right? So this gives the fit values for the probabilities for these 4 levels based on the snoring 0, 2, 4, 5. Okay, and these are the probabilities. Okay, so how do we interpret? We interpret through the beta is 0.18. So that means 1 unit increase in snoring levels. That's the snoring levels. Corresponds to 0.188 standard deviation increase in the expected value of the Y star. And Y star is a latent variable that measures the heart disease. And the larger the Y star, that means what? The more likely the person will have a heart disease, right? And here you may ask, why is 0.188 standard deviation increase? This SD means standard deviation. Why? Because don't forget, the probit link is linked to the what? Don't forget, it's the standard normal z-scores. Okay, so here, this is related to the one standard deviation of Y star. Okay, that is because of the standard normal z-scores. Okay, this slide is that's the last one. This is other binary regression models can assume different latent variable structures. Okay, and we can always, so there is a very general way to interpret the binary regression models through the latent variables. So here is the probit model, is just the one specific case. But you may ask, what about logistic regression? Can we interpret the logistic regression also through the latent variables? Yes. For the logistic regressions, it's just change the distribution from the standard normal to what? To a logistic distribution. There is a distribution called the logistic distribution. And what about others? Yes, there is other link functions available like C log log and there's some others. So we can use this similarly. So different link, if you want to interpret through the latent variable way, it just corresponds to different distributions underlying. Okay, so that's the generalization for the, so the section 5.5.5 to 6 is a generalization for this probit model interpretation to other link functions. Okay, any questions? Okay, before we end, this is the homework for the chapter 5. I've already posted, let's see, I've already posted in the Zoom. So, I mean, in the Moodles, so you can see the homework 4. And also, I've already have that in the, put that in the Moodles, and this is due from by March 19th. That's 1 week from today. Okay, so read chapter 5 in the textbook and also work on these 4 questions and submit it through the Moodles. Okay, and you can start to prepare for the exam 2. Exam 2 covers chapter 4, 5, 6. So we've already finished the 4 and 5. And the form for the exam 2 will be very much the same as exam 1. And we will talk about more details later. Okay? Oh, how many homeworks? The homework, this is homework 4. So that's the last homework assignment that we will have. This is the last one. So after that, I will still give you the exercises questions for the chapter 6 and others, but you don't need to return. Okay, that's the last one. Any other questions? Okay. If you don't have any question, let's stop here.